Alright, hello everyone. We're going to discuss the horizontal and vertical transformations of a transformed periodic function, specifically transformations of the graphs of sine theta, cosine theta, and tangent theta. So we have the form at the top of the page. Again, f is periodic. Think of the original function f as being sine theta, cosine theta, or tangent theta. Then the graph of y equals capital C times f of capital A times the quantity theta minus b, and then outside the parentheses plus capital D is obtained from the graph of y equals f of theta by performing the following transformations. Now, if you have a periodic function, the wording is slightly different here. Instead of calling it a horizontal shift, if your function is periodic, we now call it a phase shift, and it's going to be a phase shift of b units right if b is greater than 0, and absolute value of b units left if b is less than 0. So what you typically do when you transform these periodic functions is you find what's called the fundamental cycle, and we'll get there in just a moment. And then what the phase shift tells you is where the fundamental cycle of the transform function will begin. Okay, now after you've determined where your fundamental cycle of the transform function begins by considering the phase shift given by capital B, there is a horizontal scaling by a factor of 1 over the absolute value of A. It is possible that A could be negative, so in that case we put the absolute value around A just to do the scaling first. If A is negative, there would also be a horizontal reflection taking place. So the horizontal scaling by a factor of 1 over absolute value of A. And then make sure you review when the scaling is a stretch or a compression. If the absolute value of A is greater than 1, it's actually a compression. If the absolute value of A is between 0 and 1, then it's actually a stretching. Now, the period will be denoted by capital P, and that's going to be 2 pi over the absolute value of A if f is sine or cosine, and the period will equal pi over the absolute value of A if f is the tangent function. Okay, so the reason being for this, for sine and cosine, the period of those functions is 2 pi. Applying the horizontal scaling, the resulting graph has a period of 2 pi over the absolute value of A. And for tangent, since the period of tangent is pi, if you do any transformation of tangent involving a horizontal scaling given by capital A, the period then becomes the period of tangent pi divided by absolute value of A. So this is going to give you the length of the fundamental cycle. So the phase shift tells you where the new fundamental cycle begins, and then the period is going to give you essentially the length of that fundamental cycle. There is also now going to be a vertical scaling of, or vertical scaling by a factor of the absolute value of C. When the absolute value of C is greater than 1, it's a vertical stretch. When the absolute value of C is between 0 and 1, it's a compression. So you're going to want to make sure that you, again, review how transformations work. That can be found in section 1.5 in the textbook. Now, there's something called the amplitude of a trigonometric function, specifically sine and cosine. Now, if you look at the graphs of sine and cosine, half the distance between the maximum and minimum values is positive 1. Okay, so right, the graph, the middle of the middle value would be 0, the theta axis, and the distance from that to the max or min value is positive 1, and the amplitude, half the distance between the minimum and maximum function values, is also given by the absolute value of c. And then lastly, there's a vertical shift of d units up if the d is greater than 0 and its absolute value of d units down if d is less than 0. Now the vertical shift is going to give you the middle value of your transformed function. So without the shift, right, if you just had sine or cosine, the middle function value is always 0. And then by shifting up or down, you're just shifting the middle value of the function. And then once the fundamental cycle has then been transformed and graphed, you can complete the graph of the function by making copies of the fundamental cycle. Okay, so let's now take a particular example here, and let's just first focus on the horizontal transformations. For this function g of theta, which is a transformation of the graph of sine, we're going to find the period, phase shift of g, and sketch a graph. Okay, now, one thing that's always a good idea is before you even start applying these transformations, it's a good idea to at least write down your fundamental cycle for sine of theta. Okay, so there's the vertical axis. Oh, I don't like that. Okay, so here's the vertical axis, here's the horizontal or theta axis. Again, I don't like that. There, that's a little bit better. There's positive 1, here's negative 1, and here's your theta axis. And what you do is you always, your fundamental cycle of sine goes from 0 to 2 pi. Halfway between is pi, a quarter of the way is pi over 2, and 3/4 of the way is 3 pi over 2. So the fundamental cycle can always be broken up into fourths. Okay, and then 1/4 of 2 pi is pi over 2. Now sine starts at 0, increases to positive 1 at pi over 2, it's back to 0 at pi, it's at negative 1 at 3 pi over 2, and back to 0 at 2 pi. So here's a fundamental cycle of the graph of sine. Okay, now before we can find the period, let's go ahead and maybe simplify this function g of theta. We need to write it in the form that was presented in the previous slide or previous page. You need to factor out the 2, that's going to be your a, and what you're left over with is going to be theta minus pi over 2. Okay, so the period here, p, is going to be 2 pi divided by the absolute value of a, which is 2, so now the period is pi. Okay, now that agrees with when a is 2, it's really a compression by a factor of a half. If you compress an interval of length 2 pi by a half, it becomes an interval of length pi. And then the phase shift, since b is going to be this value of pi over 2 right here, that's my capital B. So the phase shift is going to end up being pi over 2 units to the right. Okay, so what that means is your fundamental cycle is going to start at pi over 2 units on the theta axis, and that cycle is going to extend over an interval of length pi. So now we're ready to graph this thing. Okay, now another good idea is to split your interval into, or your period into fourths. Okay, so what I'm going to do, I'm going to start sketching a graph of this thing. Okay, so I'll just maybe draw the fundamental cycle Okay, so the max value is still going to be 1, the minimum value is still going to be negative 1. Okay, so the vertical, all the vertical transformations really do is they change the amplitude, the distance from the middle value to the max value, and then they also, the vertical shifting is going to change what the middle value is. But here the middle value will still be 0, the min value will still be negative 1, the max value will still be positive 1. So, what we're going to do is, I'll label my pi over 2. That's where my fundamental cycle of g is going to begin. And then what I'll do is I'll increase that by increments of pi over 4. So here's another value, and that brings me to 3 pi over 4. Another pi over 4 brings me to pi. Another pi over 4 brings me to 5 pi over 4. And finally, one more quarter period brings me to 6 pi over 4, which is really 3 pi over 2. It's tough for me to squeeze this one in here, but this is really 3 pi over 4 right there. Okay, now what does sine do? Okay, wherever its fundamental cycle begins, it starts at its middle value, so at 0, and then a quarter way through the period it goes to the max value of positive 1, back to the middle value another quarter of the way through the period at pi, down to negative 1 at 5 pi over 4, and then finally throughout its whole period of length pi it would be back to 0, and there's your fundamental cycle. And then I could extend this, I could keep going pi over 4 units to the right and left, and I could keep drawing, this function would bounce back from its middle to its max, to its middle, to its min, back to its middle value. So what I'll do in the video here is I'll just graph one fundamental cycle of the transform function. Again, this is supposed to be the theta axis, and this is a graph of g of theta equals sine of 2 theta minus pi. Okay, so now for part B, in that example, let's sketch a graph of h of theta equals tangent of pi over 3 times theta plus 2. So again, before I even start, I will draw a fundamental cycle of the graph of tangent. There's the origin, here's your theta axis. Now remember, the period of tangent is pi, so what we'll do is we'll go halfway through that period, pi over 2, that's where the vertical asymptote is, and then there's where our period ends. See if I can even draw a very good dotted line here. Okay, so there's the vertical asymptote. Now what tangent does is it increases from the origin and approaches its vertical asymptote of pi over 2. And then to the right of pi over 2, the graph increases until you're back to 0 at pi. So there's a fundamental cycle of tangent theta. The period is, well, the period of tangent is pi divided by a, which is pi over 3. Divided by a fraction is the same as multiplying by the reciprocal, and the period of this function is positive 3. And the phase shift is a shifting of 2 units to the left. Okay. So the asymptote goes 2 units to the left. The I guess you can think of it this way. Actually what's going to happen is the period is an interval of length 3. Halfway through tangent's period is where the vertical asymptote is going to be. And we're just going to, first we're going to shift this graph 2 units to the left for the phase shift. And then our period's going to be an interval of length 3. Okay. So, give me a second while I fix this and make myself more room. Okay, so here's the set of coordinate axes. The horizontal is the theta axis. I have we're going to shift the fundamental cycle of tangent 2 units to the left. So this time the function is going to start at 0 at -2. Since the period is 3, we only need to graph a fundamental cycle from -2 to 1. Here's the vertical asymptote is going to occur halfway between -2 and 1. The graph is going to increase towards its vertical asymptote of -0.5, and then to the right of the asymptote the function is going to increase until I get to 0 at 1. And then just for emphasis I'll draw one more fundamental cycle, so I'll go 1, 2, 3 units to the right. Okay, add 1.5 to that, right about here at 2.5 is when you're going to get your other vertical asymptote. The graph is going to increase, approach that vertical asymptote, and to the right of the vertical asymptote, the function is going to increase until you get to +4. Okay, so there would be a graph of tangent pi/3 times theta plus 2. Okay, so there we go. There's how some horizontal transformations work. You start with the transform function, you can sketch a graph. In the next example we will start with a graph and try and determine an algebraic form of the function. Okay, so example 4 from the handout. Here is the graph of a, well, it's either a transformed sine function or a transformed cosine graph. In either case, this is a periodic function. We're going to come up with two forms for this function. So one, we're going to treat this as a transformation of sine. The other, we're going to treat this as a transformation of cosine. Okay. So a couple things we'll have to do is, first, if we're going to try and find a form sine of a times, I'm going to change the notation. So instead of using x as the independent variable, I'll use theta. Okay. So first thing is, looking at the graph, let's try and identify, if we're going to use sine, we have to try and identify a fundamental cycle, okay, wherever it makes a cycle. Now, I'm going to go over here at -2, we start at its middle value. This function increases, decreases, and comes back to its middle value at +2. Okay, so that's an interval of length 4, so the period here is equal to 4. Since this graph has been, this is a phase shift of the graph of sine 2 units to the left, our value of b is going to be -2, negative because we're going to the left. And remember, we know that the period is 2 pi over the absolute value of a. Here we can just take a to be positive. That equals +4. So solving for a, what's going to happen is you're going to get a has to equal pi/2. Okay, so there, we're done. The first form is going to be, this could be viewed as a graph of sine of pi/2, and then in parentheses theta minus -2, which becomes a theta plus 2. Okay, so there's an algebraic form in terms of sine for this graph. And then now we'll do the same thing, but treating this graph as a transformation of cosine. So let me reset the image and get all of this out of the way. Okay, so now for the second part of the question, what if I now want to view this as a transformation instead of cosine? Okay, now cosine starts at its maximum value of +1 and then first decreases. So if you look at the graph, up at -1, +1, the graph starts decreasing, increasing, and gets back to its maximum value at +3. Now you'll notice the period is still 4, and just like in the previous problem, that's going to give us that a equals pi/2. Okay, and then this time, if you look at the graph, cosine usually starts at its maximum value of +1 and decreases at 0. This time we started at the maximum value of +1 at -1. So the phase shift was 1 unit to the left, so b is going to equal -1, and the function that works is cosine pi over 2, and then this time it's going to be theta plus 1. Okay, so there is, viewing this graph as a transformation of cosine, the form would be cosine of pi over 2 times the quantity theta plus 1. Okay, so now before we combine horizontal and vertical transformations, let's just do an example or two just focusing on the vertical transformations. Okay, so vertical transformations, example 5. We're going to find the amplitude, the vertical shift, and then sketch a graph of f. Okay, so f of theta is going to be minus 3 cosine of theta plus 1. So notice nothing is being multiplied or added to the theta, so there's no horizontal transformations. So the fundamental cycle is going to stay the same. We're still going to be able to sketch this from 0 to 2 pi first. We just need to mess with the maximum and minimum values as well as the middle value given by the vertical shift. So first of all, the amplitude. Let me do this. Okay, so let's go ahead and do an example of a vertical transformation. So we're going to graph negative 3 cosine theta plus 1. Notice there's nothing being multiplied by or added to the theta, so we are not going to have any horizontal transformations, meaning the fundamental cycle is going to start in the same place and have the same period. It's just the maximum and minimum values change as well as the middle value itself. So first the amplitude. The amplitude is the absolute value of capital C, which is equal to the absolute value of negative 3, which is positive 3. That means that is the distance from the maximum value or the minimum value to the middle value, which is given by the vertical shift. The vertical shift is up 1 unit because capital D here is positive 1. Okay, so now the vertical shift gives you your middle value, and it's something that I like to call the midline. It's not a term used in our textbook, but it's going to be the horizontal line y equals 1. So that's going to be where the middle value of our graph crosses through, and then the maximum value is going to be from y equals 1 going up 3 units and down 3 units. Now also notice that since C is equal to negative 3, there is also a vertical reflection. Okay, so when I go to graph this thing, let me straighten that out a little. Okay, there's my theta axis. Our fundamental cycle is still 2 pi. Always break up your fundamental cycle into fourths. Now, the middle value is going to be up here. I like to draw a dashed horizontal line at y equals 1, if I can actually do it. Okay, so that's positive 1. Here's positive 2, positive 3, positive 4. Okay, so 2, 3, 4. And then we'll also go down. I think we need to go to minus 1 and finally minus 2. Now cosine typically starts at its maximum value on its fundamental cycle, but since C is negative 3, there's been a vertical reflection. So from the midline, since the amplitude is 3, I'm going to go down 3 units till I get to negative 2. A quarter way through cosine's period, you will be at the middle value. Probably a good idea if I change colors here for this. Okay, so a quarter way through the period you're at the middle value. Once you get to pi, usually you're at your minimum value, but because of the reflection, we are now at our maximum value of positive 4. And then you're back to your middle value at 3 pi over 2, and then you'll be back to your minimum value at 2 pi, and the graph is going to look like this. Okay, so there's a fundamental cycle of -3 cosine theta plus 1. So again, for the vertical transformations, I identify the vertical shift. That gives me the middle value, or what I call the midline. The amplitude tells me the distance from that midline to the max or min value. And then since c is negative, instead of starting the graph at its maximum value like cosine usually does, we start this graph at the minimum value of -2, increase to 0 at pi over 2. Halfway through the period we'll be at our maximum value of 4. At 3 pi over 2 we're back to the middle value, and then finally at 2 pi we're going to be at the minimum value of -2. So there's a fundamental cycle of this graph. So one more example for this video. I'll post another video tomorrow morning combining the transformations. We'll do an application problem. Okay, so one more example. Actually, folks, I lied. So that was the one example of a vertical transformation. So what I'll do is I'll put this on hold. I'll do examples 6, 7, and 8 tomorrow morning, talking about how to combine transformations, and we'll do kind of both approaches. We'll start with the function in algebraic form, sketch a graph, and then we'll also be starting with the graph and trying to identify a algebraic form, and then finally, example 8, we'll be modeling height on a Ferris wheel with a periodic function, either a transform sine or cosine function. So everyone have a good day. Stay tuned for the next video. If anybody has any questions, let me know. Thank you.